Good morning, everybody. I was waiting for a bit for seeing the numbers in the participant list. That's why for a moment I was silent. So again, welcome everybody. This is Casirigo from the ENAF Institute for Radio Astronomy in Bologna, Italy. And on behalf of the organizing committee, I'm very happy to welcome you to the third series of the EVN seminars focusing on high angular resolution science, radio science. I want to mention just a few logistics before we start. So you will be muted throughout this seminar, but you are very welcome to write your questions in the Q&A box of the Zoom at any time. Note, though, that we will answer questions only after the seminar. And we apologize in advance if we may not come to your question because of the time. So now I will hand over to Anna Bartkiewicz from the Nicolaus Copernicus University to introduce our today's speaker, Ross Burns.
Thank you, Kazi. It is my pleasure to introduce Ross Burns, who is postdoctoral researcher at the Star and Planet Formation Laboratory in RIKEN in Japan. His PhD about radio maser VLBI observation was awarded by Kagoshima University in Japan. Next, he worked at JIVE as an EVN support scientist and later moved back to Japan as an East Asia Core Observatories Fellow and later a postdoctoral researcher at National Astronomical Observatory of Japan. He has been the lead coordinator of the Maser Monitoring Organization, M2O, since it was established in 2017. He is principal investigator of the EVALS project related to collaboration with VIRAC in Latvia and director of the Global Emerging Radio Astronomy Foundation non-profit organization. Now let's move to the seminar. VLBI observation of maser flares by Ross Burns. Yeah, we can see your sharing.
Okay, can you hear me fine?
Yes, very well.
Great. Thank you so much for the introduction, and thank you for giving me the opportunity to give this talk. Like Anya mentioned, so I worked at JIVE a long time ago, so I've been friends with a lot of the people here and miss you all very much and would love to meet you all again soon. So I'm going to talk about VLBI observations of maser flares. And I had a introduction slide, which I guess I don't really need to go into in detail, thanks to the introduction already. But I kind of wanted to mention, while I was in Kagoshima, I was mostly focusing on the Vera radio telescope or VLBI array. And obviously, while I was at the EVN, I was focusing on the EVN European VLBI array. And since then, I've been using the LBA, VLBA, and KVN, and Kava. And one thing I kind of want to congratulate the EVN on is their support for observers is second to none. And I think that if you are a new user of VLBI, you're interested in doing VLBI, definitely consider using the EVN because you get a lot of support from start to finish, which I think you not to criticize the other arrays, but you just don't get that level of support as you do with the EVN. So yeah, if you're interested in doing VLBI, definitely consider using the EVN for that. So I'm going to talk about masers, and I think it's important to start with, what is an astrophysical maser? And it's essentially a cloud of molecular gas. And there's different kinds of chemicals that can be masers. So you can have hydroxyl or ammonia or SiO. There's a lot of them. The ones that you most commonly see in an astrophysical context are hydroxyl, methanol, water, and SiO. So these are clouds of molecules that are 100 to 100 AU size, probably bigger as well. But they have a special property, which is that they have population inversion. So population inversion, if you did maybe high school or university physics, you know that molecules have different energy levels. And in a Boltzmann distribution, or like a typical cloud of gas, you'd expect most of the molecules to be in a low energy state, and then some of the molecules to be in a slightly excited state, and then even fewer molecules to be in an even more excited state. So that's the kind of typical cloud of gas. in the case of population inversion, you have some kind of energy source that is lifting the molecules up to the higher energy level. And then they're falling down very quickly to this energy level, but then they can't fall down very quickly to the lower energy level because, they cascade down. So what this leads to is this pileup of excited molecules at the energy level here. And this is an inverted version of what you usually get. Usually there's more at the bottom and fewer at the top. Now there's more at the top and fewer at the bottom. So this allows you to do something interesting. So your cloud of gas has a population inversion of the molecules. And this is represented, say, here. And if you have an incident photon coming in that has the same energy level as the difference between these two energy levels, you can induce the de-excitation of this molecule. And what that's going to do is going to produce another photon at that same energy level or the same frequency. So one photon comes in, two come out. Now, if you imagine that two come in and four come out and vice versa, the more times you can have this process repeat as the photons go through the cloud, the much brighter your maze is going to get. So it's going to be exponentially brighter. So regarding these masers, the different ways you can have changing your maser brightness, you can have more photons come into the maser cloud. You can have more enhancement in the pumping conditions, which create this population inversion, or you can increase the path length of the maser cloud, which then allows you to, like we said before, you have more instances of stimulated de-excitation. And then that comes into your radio telescope and you measure it and you do some science. So what are the kind of places where you can find masers? There's a lot, there's like comets, planetary atmospheres, mega masers, all these kind of things. But I think the ones that get spoken about the most, at least in our circle, is the protostars and the evolved stars. So protostars, you have a kind of disk, and your protostar is forming in the center of the disk, and then there's a jet that's launching from somewhere in the inner regions of that system. And in the case of evolved stars, you have some dying star here, and it's blowing like bubbles or like shells of gas and dust as it's dying. And in those regions, you can have masers because you have the right physical conditions to produce masers. So in the protostars, typically in the disks, especially in the case of high mass stars and a particular class of methanol masers, you get them in the disk. And then water masers, they typically are powered by shocks. So I mentioned, but you have to, increase the molecules up to the higher energy level and they cascade down. The way that you produce that lift of energy in the case of water masers is shocks. In the case of SIO masers and some of the methanol masers, it's radiation. So the radiation pumped ones, they're near hot things or bright things, and the collisionally pumped ones are near shocks. So that's kind of a very, very simplified view of where you see masers. And this is important because if you're looking at, say, an SIO maser and you see that it changes in brightness, then you can consider that perhaps the radiation in that region has changed. Vice versa with shocks and the water masers. So this kind of brings us to the MTOR. The MTOR is the Maser Monitoring Organization. So we're people that monitor masers. And this began in 2017 in a symposium, an IAU symposium about masers. So the world's experts and people, astronomers interested in masers, they gather once every 4 years or so to talk about masers and show their recent results. And what we kind of realized in this meeting was that there were a lot of radio observatories that had been monitoring masers for like decades. And they saw instances where the maser suddenly got very bright and then died back down. And they would typically publish their results every 5 years or so, or even longer. And the unfortunate thing about that is that you don't have a chance to kind of follow up those observations and see what's happening, because it's already happened and finished by the time that they publish their paper. So what we realized is it would be good to have a better, say, communications platform so that we could actually alert each other to these transient events. And that was the M2O. That was the kind of the beginning of it. And then something crazy happened, which is, you have all of these maser experts in one room in Italy, trying to get over their margaritas from the night before. And suddenly there's news, we got a telegram of this huge maser flare, which was seen during the conference. You have all the experts in one room, and it's the perfect time for us to think about how to respond to this. So we did. There were two maser flares, actually. One was in a source called G25 and another in a source called W49N. And they were going from a couple of hundred Janskis to tens of thousands of Janskis. You don't really have to know what these mean just to understand that it went from something to something much brighter. And what you're looking at here is the velocity of the masers. So you can imagine, just imagine for imagination's sake, that your maser, your protostar has a velocity of about 50 kilometers a second with respect to you. Then these ones are moving towards you, and these ones are moving away from you. And they're still the same water masers. It's just showing the velocity with respect to you. So what we did is we arranged some EVN observations to see what's going on in this maser flare. And going back to that spectrum, so you saw the peak earlier in G25. This is zooming into that same peak. Using the EVN, we imaged this emission, and we found just a very, very, very small blob. So this is a very, very high resolution observations, this milliarc second scale. We didn't see anything particularly interesting and was kind of disappointed. But when we imaged the wing emission, we found that it split into two. And so we kind of figured this out. We were like, hey, what's happening here is you have two maser spots or two maser clouds that are moving in front of each other in the line of sight. And as they do, there's an overlap. And we mentioned about the path length earlier. So if you increase the path length, the maser gets exponentially brighter. So you're having photons coming into a maser cloud, getting amplified, then coming out of the maser cloud very bright, and then going into another maser cloud, getting amplified again. So in that location of the overlap, you get extremely bright emission, and that's what we're seeing here. And this is the not overlapping parts. So we figured that out, and we got a nice paper, which was published on my birthday, so I was very happy. And we were like, yeah, okay, so these follow-up observations of maser flares is interesting. Let's keep doing it. And that's kind of how the M2O really started. So fast forward to more recently, we have more than 100 members, 26 papers as of last time I checked, but it's always increasing. 3 of those are in Nature Astronomy. We followed up about 19 maser flares. There have been more than 19, but some of them we determined were not worth following up just because we didn't have the resources or time maybe at the time. We typically see about 2 flares per year of each of the water and methanol masers. So to find these flares, we have a network of radio telescopes that are monitoring for masers. And these telescopes actually have been doing this for a long time. They didn't do this since the M2O. The M2O is basically just the joining of these efforts that already existed. And depending on their time resources and such, they are monitoring, a certain number of sources. Depending on their receivers, they're, observing at certain frequencies. You can see here a kind of global distribution of the radio telescopes that are reporting to the M2O. You notice that there's nothing in the US, but we're doing something about that now. So we should hopefully have about 2 stations in the US to add to efforts. And this is the sky map. So this is showing where the water masers are in blue. You can see they're kind of spread mostly in the northern hemisphere here. And then the methanol masers, which trace the high mass stars, they're kind of stuck in the galactic plane where you'd expect them to be. So how does the M2O work? Well, we have these radio monitoring stations, and there's a lot of them with a lot of different frequency receivers. We have people doing interferometry and VLBI, infrared, near-infrared, and theorists who can try to help us understand the results we get. So the monitoring stations, they find a maser flare and they report it to the M2O. The M2O then shares this information to everyone, and we initiate follow-up observations. And then we collect our results, we compare our results and discuss things, and we try to publish and explain what we've seen. And a rule that we have developed in the M2O, which I think is very important, is the team that discovered the maser flares, the radio telescope, which, like I said before, they typically publish once every 5 or 10 years. They must be credited with the publications that come from this particular event. So rather than getting one paper every 5 years, they might get 5 papers in 1 year or something, which is a lot better for them and their longevity. And it also incentivizes people to report these flares to us. So this monitoring is the backbone of the M2O. And there's a wonderful resource called the MaserDB, or the Maser database, which databases all of the known masers in the sky. And we can compare the source list, or the sources observed by the M2O, with all of the known sources from the MaserDB. When we do that, we see that the 6.7 gigahertz methanol maser, so these trace high mass stars, we're monitoring about half of them. And in case of the water masers, we're only monitoring about 10%. So even though we're probably the biggest global effort in doing this, we're still not even at halfway, say, capacity. We're trying to do things about this. We're trying to increase our monitoring resources. But despite the kind of progress we've made, there's still a lot more progress that I think could be done if we had more facilities. When we find those flares, we have to follow them up. So we have about 14 telescopes looking for flares, and then we have experts that can tell us, if you see a flare in this transition, maybe you want to check this transition as well, things like that. And then we have to go and image, or go like a hunting to see what actually happened in the star-forming region, or in the whatever progenitor is causing the flare. So to do that, we have to maintain a pile of resources for follow-up observations. So this is basically you trigger observations on a something like the EVN to say, we would like to observe this maser flare. And we kind of maintain these for a lot of instruments. Some of this list is outdated. Sophia, unfortunately, was grounded. But to make up for what we don't have, we're trying to collaborate with other large telescopes or other campaigns and projects. And this has proven quite fruitful so far. I want to talk about high mass star formation, because this has been our biggest breadwinner in the M2O by far. Unintentionally, it just that's how it turned out. The high mass stars are the only places where you have the 6.7 gigahertz methanol maser. This is a fantastic tracer, because if your source has 6.7 gigahertz methanol maser, then you have a high mass star there forming. And your high mass star is forming in a disk, and the methanol is going to be somewhere in the disk here. So the current thinking on high mass star formation is that rather than the star just accreting material slowly, it's actually in a kind of low state of accretion for most of the time. And this is interspersed with bursts of accretion, where a lot of material piles on from the disk onto the star in a short amount of time. And so that's kind of represented by this blue line against time here. That's the accretion rate against time, showing you these bursts. And the mass of the star then becomes like a step function, where it's going up in steps and then nothing for a while, then a step. To get this kind of scenario, what is thought to be needed is a gravitationally unstable accretion disk. And we've seen those in the low mass stars, but it wasn't really seen in the high mass stars. So this was something that we were looking for. While this has been simulated and modeled, there's only been 5 published observationally confirmed accretion bursts in high mass protostars. So high mass protostars are rare, they're hard to observe, and their accretion bursts are, a few % of the time of their existence. So it's really, really lucky if you find one. 3 of the ones that we have seen so far were traced by masers. So maser monitoring is proven to be a driver in this entire research field. And I think the reason why it's a lot easier to find accretion bursts with masers is, one is economical reasons. You have these radio telescopes all around the world. Some of them are refurbished telecom dishes, and they can do a maser observation in a couple of minutes. Whereas if you wanted to monitor the infrared and you wanted to do it at a high resolution, it's going to be very hard to get the observational resources. when you have an accretion burst, I should mention the infrared and the methanol maser will expected to increase in brightness. And that's seen in past examples. So you can see here in time, the methanol maser got very bright and then start dying down in S255. And in the near-infrared continuum, we think it went up and then it's going back down here. So methanol masers, they're really easy to observe. You can observe a lot of them. We know where they are. They respond very sensitively to changes in their environment. So they're kind of the ideal tracer for accretion bursts. And we started kind of honing in on this. So for a case study, I want to mention G358, which has been probably the source that we've got the most information out of so far. So this is the methanol maser emission, and this is coming from these methanol masers in the disk of a protostar called G358. And you can imagine that the protostar velocity is somewhere around here. So some of these masers are coming towards you and some are going away from you. And these are the days shown here. So you can see this emission is changing on day scales. You have to bear in mind that we used to think that star formation was a process that happened over thousands or millions of years. And this thing's changing on days. So this is kind of a big paradigm change that we're seeing in high mass star formation, is this transition into the time domain radio astronomy. So we saw this event. This was discovered by the Ibaraki team, and they report to us. And so we did our thing, and we start doing follow-up observations. So we start looking with other radio telescopes, with other receiver frequencies to see if there's other masers. And this is some results from Harderbystock in South Africa. They found the 6.7 gigahertz was flaring. So this is showing you time here, brightness is in color, and then the velocity or frequency is on the y-axis. So you can see this flare up and then die down. At 12 gigahertz, you see it flares up and dies down. And then there's other transitions that are typically not seen at all. And they flared up and died down. And transitions that we didn't even expect would exist, and they flare up and die down. I think you can notice that we started this one late, and I think the reason is we didn't even think to check until this point. I might be wrong with that. But we found a lot of new maser transitions in this way during this G358 event. To come on to the VLBI results, typically I would mention about the infrared results and things for G358, but I think in the essence of time, I'll go straight to VLBI. So we got the flare alert from the M2O, and we did the follow-up observations with VLBI. And so we used the VLBA, which is in the US. It's a bunch of radio telescopes across the US, which you combine to make a big telescope in the same way that you do with the EVN. So you have a bunch of telescopes originally across Europe, but now across the world, which you combine to make an interferometer. So we also used the Australian long baseline array and the East Asia VLBI network. And this is our first image of what we saw when we followed up and did a VLBI image of G358. So this is the same 6.7 gigahertz emission, methanol maser emission, that you see in the accretion disks. But now this is being seen at milliarcsecond scale. This white cross is showing you the position of the millimeter core center, which we saw in ALMA observations, which were also done as follow-up actually for this entire campaign. The colors here, like I've mentioned before, they're showing you the velocity of the emission with respect to you. So the blue emission is going towards you and the red emission is going away from you. So you can kind of get an impression of rotation or expansion or something is, things are moving here. And it doesn't look like a circle, but there's a hole in the center and there's stuff around the outside. It looks a little bit like a ring. Anyway, so this was really exciting. So this is the first time we saw, a VLBI image of the methanol maser emission during a accretion burst in a high mass star. So we did more observations, and you can see the days here trailing onwards, and these are the different telescope arrays that we used. And we're looking at the same emission in the same protostar. This white cross is the same white cross, the coordinates are the same, velocity scale is the same. And you can see that this ring of emission is getting further and further away from the star. If you put that in context of this maser monitoring result I showed earlier, you can see that we started the VLBI images at the very beginning, and we managed to kind of trace a lot of the different stages of the flare, including the end. And the interesting thing is this kind of ring of emission stops really being there at the end. So the ring really only existed during the main part of the flare. What we think we're seeing is a kind of heat wave of emission. And so what do I mean by heat wave? So I mentioned before about how the methanol masers, they respond very sensitively to physical conditions. They need a particular temperature. And if you heat up the center, then that temperature where, bearing in mind that the outside is cold, the center is warm. If you have an increase of heat in the center, the radius at which the heat is right for masers is going to gradually propagate outwards. So what we're seeing is not a motion of gas here. We're seeing a motion of heat, which is exciting the gas to make masers as it goes through this disk. And you can see that quite clearly. So this is 3 epochs that are plotted here. And you can see that the radius of this maser emission plotted against time shows that there was a sudden increase in the region or the size of the region where the masers are. So that the ring just got really, really big and then kept getting bigger. But it was doing this at like a few percent of the speed of light. This is like absurd. It's like super fast. Like I remember in my PhD, we were talking about like kilometers per second kind of speeds. And I thought that's crazy fast. We're now talking about like percentages of the speed of light. So this is absurd. It can't be methanol gas moving because that gas would have been thermalized and messed up. So we very quickly realized that this was not a propagation of gas, but a propagation of heat. And so we called it a heat wave. And we actually had like a really cool idea after this, which we never planned to do. You have these different rings of emission that's being traced by the methanol at different times. And so like say like red is representing this one and orange is this one and so forth. If you add all of these up, just like, add them up in an image, you can see a kind of sparsely sampled map of the disk. And so that's what we did. We just added up these images, VLBI images from different arrays. And we saw for the first time a milliarc-second map, essentially, of the methanol maser emission in an accretion disk of a high mass star undergoing an accretion burst. So this was the first time this happened. And we could see some structures, you could see this kind of spiral arms and things here. And we did a lot of fitting. There's a lot of math involved and stuff, which are too boring to really go into. But these VLBI observations, this could not have been done at without being VLBI. Like you need this VLBI resolution in order to get this kind of fine detailed structure on these substructures in the disk. So this gave us our third Nature astronomy paper. And the interesting thing is how well this matches the gravitational instability predictions for episodic accretion in high mass stars. So we were really, really lucky with this one. I'm not sure we'll ever be this lucky again, but we got essentially, we got a Keplerian disk with spiral arms in a high mass star that's evidence of gravitational instability. So like VLBI just absolutely shone through, and it was amazing because like all of these are predictions from theories that have existed for decades, and we managed to find observational evidence of all of them in one data set just because of, thanks to a lot of people working towards this effort. So we managed to get our nice Nature paper in Nature astronomy paper for that one. And this kind of brings me to the methanol masers. So we did notice some really weird behavior. And the weird behavior is that you can model the expected brightnesses of the different transitions of methanol or the different transitions of methanol masers. Let's say your gas is 300 Kelvin, you would expect the 23 gigahertz transition to be this bright, and you'd expect the 6.7 to be this bright and so forth. So these models exist, right? And from that, if you can prove that the methanol emission is coming from the same cloud of gas, then you can make comparisons of the observations with these models. And I think this is a nice example here. This is, again, G358, where you can see that the 6.7 gigahertz methanol masers and the 12 gigahertz, is both in these models here, do indeed overlap in a lot of, or most instances in the sky. We were also able to see, for the first time, some VLBI maps of some very, very rare or new maser transitions. This is some nice work from Gabo Oros, a good friend of mine, showing a 7.6 gigahertz methanol maser, which I didn't even know that existed until we accidentally found it. I say we, I'm not really involved in that very much. But a lot of these strange transitions just showed up in G358. So we noticed that, G358, yeah, it's really unconventional because there's no model or there's no set of parameters that would give you typically a 6.7 gigahertz maser that's not brighter than the 12 gigahertz maser. You see, like, this line is always lower than this line. But that's exactly what we saw in the data. So we might need some new maser models, or we do need some new maser models for these non-stable or changing environments. And I think another big outcome of all of this research is that a lot of people who are doing any kind of star formation modeling or simulations, they do need to factor in that the physical conditions are changing thanks to these accretion bursts. They're changing drastically as well. It's one of the things we've learned from the M2O, and I think that if there's anything that we've served the community with that has the most value, I think it's highlighting these temporal changes in the physical conditions in these star forming regions. And I'd like to give a few examples of those. So here's another source that we were monitoring, and we saw the flare and we followed it up a couple of months ago. So this is a maser that was stable for like 20 years or so, and then suddenly it starts flaring. So that's a really long time to be doing nothing and then suddenly start going crazy. So we followed it up. You can see in the ALMA images that there's kind of one big bright core here and then these smaller cores around here. And if you zoom in on there, you can find where is the maser transition, and you can find where is the methanol emission in this source. There's usually a lot of archival data you can use to get context on your VLBI images. And so the VLBI image that we got, this is the one that we got from the M2 observations. I should mention that Anya has already published a series of papers on this particular methanol maser ring. I think the jury is still out on exactly what is forming these rings. So I was really hoping that the rings that we saw in G358 were going to explain the rings that were seen by Anya's work and her team, because they found several methanol maser rings in other high mass star forming regions. And I was thinking, if the heat in the center increases, you'll see that ring move, which we didn't see. So that's really bizarre. We don't really know currently why that happened. We didn't really think this was an accretion burst. And then I checked the Astronomer's Telegram recently, and it turns out that we do think this might actually be an accretion burst. So again, I think the jury's still out on this one in particular, and we're still working on it. We've got a lot of data on this one, as we do with a lot of the other stars that we're looking at. Another nice example would be G11. So this, I should mention that the previous plot that looked like this is the Ibaraki IMET data. This is also Ibaraki IMET data. So this is showing you, if you imagine that this is the spectrum of the masers, so like I mentioned before, you have maybe the star velocity is here. These ones are going away from you, and no, towards you, and those ones are going away from you. And you pick one of these velocities, one of these components, and you track it against time. That would be this. So let's say, so that 8 and a bit is going to be this purple one. That's probably this one here. So that one is going to be that one. If you want to know how this one changes in time, it changes like that. And then Olga Bayandina, so she then did the VLA observations of this. And you can see there's like a maybe outflow cavity here and maybe a dust bridge here and a bunch of protostars. And inside here, you have this very complex maser structure. You have water masers here, continuum emission here, and methanol masers. And these methanol masers start changing suddenly. I can't talk too much about this one actually, because I think we found some very bizarre behavior. And we're going to have to kind of postpone the discussion until the publication is out, but there's really strange things happening in this particular source. With regards to the VLBI map, you can see that it looks like this, which I think you can kind of notice the similarities with the VLA map. Obviously, the VLA is a lot more sensitive, but we have a lot more resolution. And we had 3 epochs with VLBA. So we're hoping to get some proper motions on this one to see. Now, I think I see some kind of corkscrewing motion here, but that might just be a trick of the eye. I think the proper motions will determine if that's real or not. Another nice source is G359. So this was observed quite a while back. And this is actually a source that was monitored by Harder-Beestock years and years ago. And it was found to have a flare way back when. And then it did nothing for a long time. And then the Ibaraki team found it had another flare again. And you can see that the flare structure or the flare profile in terms of brightness change against time is quite similar. Note that this is log scale and this is not. So if you imagine if this was not log scale, it would just look a bit pointier. And so you can see this is actually a reoccurring behavior. So the source that is the progenitor for this maser flare is a green fuzzy. And green fuzzies are they're sources in the Spitzer catalog that are green and fuzzy. I can't really say it any other way. And that's thought to be some activity from maybe shocks or some kind of star formation related activities. If you zoom into the center of this green fuzzy and you make a VLBI image of this maser emission, you see something like this. So this one, I mean, like, you know, it's nowhere near as beautiful as G358. But what we did get from this was the maser component that was flaring was this one in the center. And possibly the flare that happened a long time ago in the Harder-Beestock monitoring might have been this one, at least if you match them up velocity for velocity. And we talked at the very start about what can change the maser flux. And I think you know, if you have like an accretion burst, it's going to enhance the pumping or maser excitation conditions in the entire region, like we saw in G358. And that's not happening here. Like most of the other masers didn't notice that anything was happening, right? It's just one component flared up. So I don't think this is an accretion burst, just based on that. Then we had the case with the maser overlap, which is an increase in path length. That could maybe be explaining this, because you have a kind of symmetric rise and symmetric fall, which is what you'd expect from a continuous, you know, like a relative motions along the sky plane that are not changing. So that would kind of be well explained in this case if you're looking at the profile. The other one would be a change in the seed photons coming into the maser, but I think that would probably affect more masers in the region. So we're probably seeing another maser overlap here, I think. We do have a heck of a lot of data, not just the VLBI data, but infrared monitoring data, VLA data. There's always like a hell of a lot of things to learn, and we benefit greatly in the EM2 from having a lot of people from different walks of life and different expertise. So there's people that can notice something and be like, hey, that's this. And like, you know, I would never have noticed that. So this kind of mix of expertise, people sharing ideas, I think is definitely helping us to get good at interpreting our own results, and then, you know, those turn into better publications, and the research community as a whole benefits. So I think I want to come to conclusions here. I talked about the formation of the M2O, and I think it's proven itself to be a valuable and worthwhile endeavor, and it's worth maintaining it and developing it. The accretion bursts that we've seen in high mass young stellar objects, they're regularly accompanied by maser flares. Not always, or maybe not always, but at least I think 3 out of 5 that we've confirmed so far have had maser flares that we saw. The 6.7 gigahertz methanol maser line is that's the one you need. I mean, that's the one that really identifies exclusively these events. And we are actually under threat to some extent from the spectrum, that the frequency spectrum of radio signals that we have, that we use as humans. There are certain parts of this frequency spectrum that are maintained for radio astronomy. And unfortunately, they sometimes get sold for industry purposes. So people doing satellite communications, they want to use these frequencies. We have this one frequency which is driving all of our work in the M2O. And I think that we as the M2O, we've contributed hugely to the understanding of high mass star formation. So it would be a real shame to see this frequency band get polluted by SATCOM activities and things. It would basically blind us. It would be like turning the lights on in your optical observatory. It would make our entire endeavors probably a waste of time. So we're really hoping that people can be mindful about that. And if you're involved in the industry at all, please tell your peers and things that this is something we do care. This particular transition is one that we do care very, very deeply about. With that in mind, the flares in this transition, they're not always accretion bursts. So like with G359, or at least that's my opinion, is that it's probably a maser overlap, but we need to confirm that. So you really do need other ways of confirming if it's an accretion burst. So you get your confirmation from, for example, the other radio frequencies, continuum, submillimeter infrared. And for that purpose, we have a lot of these people either in the M2O or collaborating with us to help us to just discern what is really happening during these events. So there's a lot of work to do. There's a lot of data to publish, interpret, comparisons, fitting, modeling, publishing. It never stops. If anything, it's getting more and more active as time goes by. But I think we are finding a lot of new phenomena. I don't think we are. We have found a lot of new phenomena. We're dealing in a field of research which is very exciting. We're confirming or refuting theories that have been around for decades, and we've just now been developing the tools to do that. So there's a lot of opportunities, and I think what we're seeing right now is a kind of renaissance in the time domain radio astronomy. Bearing in mind that a lot of these discoveries I've been talking about, they were made by radio telescopes which have been sitting there doing stuff for decades on very little money, on very little human resources. A lot of the time they were old telecommunications dishes that were taken over by radio astronomers. And so the kind of cost to reward, or the return on your investment, is absurdly good. And I think people are kind of waking up to that, and I think it's kind of driving a new time domain radio astronomy effort. And that's just something that I'm really happy to be part of. This is why we started the JARA Foundation, which was mentioned at the start, is to hope, in hopes that continues and that these facilities don't get shut down, because a lot of them are at risk of getting shut down. Just before I finish, I want to mention, thank you to everyone in the M2O who's, supporting me throughout of this. I have a lot of supporters outside of astronomy as well that are keeping me sane. And I just want to say thank you to my family and friends for, just keeping me sane throughout all of this work. And yeah, it's been a wonderful ride, and I hope it continues. And I'll always be happy to have everyone's support along the way as well. So yeah, I think with that, I'll go to questions, and yeah, I think I'm done there. Thank you very much for listening. Thanks for your attention.
Thank you so much, Ross. This was really, really a fascinating talk. So for this moment, the Q&A box is empty. I will leave some time for people to write their questions there. And I'll take the prerogative. I'm happy that I can ask some questions. So you are talking about the variability of the masers, either in the flaring or just because they vary in any case. How does this relate to timescales that we know of protostars? You know, their rotation period, if we have some idea of that, or maybe the rotation period of the disk.
Yeah, that's a really good question. Well, you'd imagine that the stars are spinning quite fast because they're getting a lot of angular momentum dumped onto them by the disk during accretion. I don't know exactly the periods. That's a really good question, but I would imagine it it's probably like days to years, no? Because I mean the sun is kind of at that time scale. Then the disk, I guess the further you go out in the disk, the longer the period would be then. I think you also have to consider things like if the maser itself, if the cloud is rotating, because then you can have changes in the maser brightness there. And I think Malcolm Gray wrote a nice series of papers. One of them was about that in particular. Is a very long-winded way of saying I don't know, but there's a lot of different processes that can give you different timescales, and I think if you are aware of those timescales and you compare that to your monitoring results, you can match them up. The super flare that I mentioned at the start, that was like intraday, so that was like a few hours. It went up thousands of Janskys and back down. So that means that a very small thing must be causing that variability. So generally, like, you know, to avoid having to say I don't know completely, like the shorter the time scale, the smaller the region that is causing it, I think.
Well, I don't know either, so I'm just very curious because we start to know so many details of these objects, and we really have to dig it out because it's really hard to find.
Yeah.
And it's amazing how the power of this monitoring and then the VLBI observations afterwards, how much information is gotten, also in combination with near infrared.
Yeah.
Do you know something? What are millimeter masers? So we know masers. You talk mainly about centimeter masers. Oh, do you know how masers in ALMA would contribute to this?
Yeah, there's
not at 90 gigahertz, for example, masers.
So we actually saw in G358, we saw that I think there's a 95 gigahertz methanol, it flared up. And I've got KVN data on that actually. But then even at the higher frequencies, like the 300s of gigahertz. So Crystal Brogan wrote a very nice paper that showed maser behavior in the G358 event. And I think if I remember correctly, about 14 new masers were discovered, and a lot of those were in millimeter frequency and submillimeter, in fact.
Oh, we have a question from Tatiana Rodriguez. Tatiana says, excellent talk. In case of water masers, do they also follow the heat wave pattern as the radiation escapes through the cavity? Or is the collisionally pumping still dominating?
Oh, that's a really good question. That's become a topic. So that's something that we're really focusing on at the moment, because we do see the water masers change. And initially what happens actually is when the heat wave reaches the water cloud that has the maser, it can actually turn off the water maser. And we think this is because, so I mentioned about the energy levels, and you have some excitation, and then you have masers drop down to an elevated level, and then they drop down again. You can block the sink that allows this to happen. And you can actually saturate the water masers out when the heat wave arrives. And we've seen that in a few examples now. The interesting thing then is that the water masers then come back after the heat wave has passed. What we then see, so the water maser is very complicated. We've seen them flare during accretion bursts. We've seen them appear. We've seen them be switched off by accretion bursts. And then we've seen when there's a new protostellar jet after the accretion burst, we've seen water masers then appear in relation to those shocks. So I think the water masers, they're kind of all over the shop. The better person to ask would be Olga Bayandina, because she's doing a lot more work into the outflows. She's doing very good work involving the methanol masers that trace shocks, the class 1, and also the water masers. But yeah, I think the short answer would be the accretion bursts affect the water masers significantly in a variety of ways, turning them on, turning them off, and then causing new masers, new water masers when there's new ejections a year or so down the line. A great question, though, really.
We have another question by Paul Fallon. Hi, Ross. Really enjoyed the talk. Thank you. Has the MTO done much work on other masers flaring at the same time as the methanol masers during these outbursts?
Yes. So the way that we've kind of been operating nowadays is like you have a flare, either at 22 or 6.7 gigahertz, and then we report this to everyone in the M2O. And then basically anyone who has a radio telescope is going to point and look at that. And if they have a receiver that other people maybe don't have, then they're going to use that. So we check as many frequencies as possible. We're all looking at the same object, maybe at different frequencies, and trying to see what's going on. And in the case of G358, yeah, we found a lot of new maser flares. Some of them were masers that are known to be transitions that are known to be masers, which then flared. And some were transitions that were not supposed to be masers, like they're not predicted to be able to do that, and they flared too. So we were seeing strange transitions of methanol flaring. Then in other events like NGC 6334, there was, I think, OH flare, water maser flare, methanol flare, like any maser that could exist did exist during that event. So we do check as many frequencies as we can. And that is kind of one of our diagnostics for whether this is an accretion burst, is if we see flaring across the board, then it's much more likely to be an accretion burst. If we see flaring in just one transition, then it could just be this overlap or some other explanation. So yeah, it's the first thing we do when we see a flare is we check the other maser transitions at other frequencies, yeah.
Thank you for answering that. So Tatjana has an additional question. First of all, she says, how interesting. Thank you so much. I have two interesting sources that I'm studying in the radio continuum and water masers. How can I know if they are being monitored by the M2O?
Great. So first, there's two things you can do. One thing you want to do is check the MaserDB, maserdb.net. So this is the maser database that I mentioned. That will tell you if that'll tell you all the past observations of your source. You put in the coordinates, it'll find your source, and it'll say, you know, this was observed in 2005, and there was 12 gigahertz maser, whatever. It'll tell you that all of the past observations. This is the first thing you want to do is that. To find out if we're monitoring it is a little bit more tricky. The only person who really knows all of the source list is me, because it's kind of not, like I mentioned before, like all of these monitoring observatories, they're doing their own thing and they report to the M2O. They might not want to share their entire source list. So if you want to know if your source is being monitored, probably just email me. Or if you see that it's monitored in the MaserDB and you find the transition, you can maybe ask the people who monitored it in the past. For example, if you check the MaserDB, you'll see if Ibaraki IMET program is monitoring it. So you can just email them directly. That's an option. But email me, email maybe Dimitri at the MaserDB. MaserDB and M2O, just contact us is the best way. Yeah, thank you for putting the MaserDB link in the chat there. Maybe we can put it in the YouTube afterwards in the comments.
Yes, I think we should absolutely do that. So we have time for one more question by Olga. Great talk, she says. Can you give us a sneak preview at any plans for the future of the M2O activities? Basically, what kind of future awaits us, in your opinion?
Okay. Well, I think that's a very difficult question, but I think we kind of got a quite large now. Is it more than 100 people? And we're moving towards a kind of focus group type environment where rather than have everyone in one room yelling at each other, not that people yell at each other, they don't do that, they're very polite, is to have these kind of focus groups where people can collaborate in a smaller, more focused, quieter environment. And so we're trying to set up like the single dish monitoring focus group, interferometry focus group, star formation focus group, the evolved star focus group, these kind of themed groups. And I think that way then you can kind of determine your own goals as part of that group and establish your resources that you have and what you want to contribute and what you don't, rather than have everything always having to be considered, having to try and consider everything all at once. It's also a lot less work for me, so that's really helpful. And we're also considering setting up a kind of seminar series, maybe not dissimilar to this, where we invite people to come and give some talks. We always talk about having an M2O conference. We occasionally do data reduction workshops for VLBI. There's a lot of things that we're doing, but I think we definitely need to kind of recuperate and make some very clear plans on the future for the way we're going forward. I would really like to get the M2O to become kind of housed in an institute somewhere, like have a project set up that can have postdocs and things like that. Because currently, everyone, all this work we mentioned so far, no one's being paid for this. This is just people contributing their time as volunteers. So it'd be really great if we could have something set up where people work on this specifically. And I am always making efforts to find something like that and also stay employed myself. So yeah, I think we have a very bright future. I think as long as you know, the 6.7 gigahertz region, as long as that is kept safe for us, we have a future. As long as we can keep these radio telescopes alive, and we're making efforts there as well, then we have a future, and I think it's a bright future. But it's a balance of fighting off the invasions into our frequencies and hardware, and then also providing space for kind of focused discussions and good support for our astronomers and theorists to do what they do, because they do a great job. I think we could support them a little bit better, potentially.
Thank you so much, Ross. We are on the hour, so I would like to thank you again, Ross, for this very, very beautiful talk, very interesting talk. I would like to thank all the participants for being here, for listening, and for joining the discussion with their wonderful questions. And now some last news from Benito.
Yes, thank you everyone for joining. This will be actually our last seminar before the EVN Symposium that will take place in September, early September 2024 in Bonn, Germany. And yeah, this will be the last seminar. As I said, we will resume after the symposium with more talks. So that will be in the fall of this year. And I hope that we can actually see you in person, hopefully in the symposium, that the registration is still open. You can log into the webpage of the QR code. So see you soon, and thank you for your attention and participation here.
Goodbye. Have a nice day.